Hey, everybody. This is Steve. I'm going to be having a little hangout on math today. I invited a bunch of people. I don't know where they're at, but we got EO who actually teaches math. So he's going to be my my go-to kind of guy as we follow through on this a little bit and discuss what a Taylor series is, kind of how to find what the Taylor series is for e to the x and why the derivative of e to the x is equal to e to the x. Now, let me reiterate before I start this. I am not a math guy. This is a layperson's attempt at this to explain it. Although I've had it before, it's been several years. So do not take what I'm going to say as gospel. This is not a rigorous proof, and it is circular in some ways because I have to assume the derivative exists for e to the x is e to the x by coming up with the Taylor series. And so the first 3 pages that I have for this, as we go through it, it's circular. I get this. I understand that. This is not rigorous. But the only way I could really try to explain to people why this works, and that's my whole goal, is explain what is actually we're trying to do, what is a Taylor series, and how does it get us to where we want to go, and why taking the derivative of that. The proof that I'm going to use is a very informal proof. It's not sound enough to be used in a rigorous form. I have talked to, I looked at a PhD in math, look it over. We've already discussed these issues. I was aware of them beforehand, but this is just for educational purposes.
It's a heuristic. It's a useful heuristic.
It's heuristic. Yeah, I like the way you put that. It's heuristic. So it's conceptual. So the link to come in is out there. A few people have it. I don't want to look to other things as I'm going through this because it's be hard enough to focus on this. So if anybody has a link like EO or Drag, or I give it to Jade, give it out to Hogtie, whoever else who wants in. So anyways, we're gonna jump right into it. I'm going to be screen sharing. I'm actually going to be pulling some things over from different screens here. And then I'm going to be showing you kind of what we're going to be doing here. So let me screen share. Okay, present. So make sure the outside chat can actually see this. Make sure it's clear. Make sure it's large enough where they can see it. I'm going to blow it up a little bit here. And then we're going to see where we're actually starting from. And then while we're doing that, I'm going to put the video over here. I don't need that. And I need the live. I got to find the live chat so I can at least see. Yeah, one sec. Let me get organized here. Where's my live chat? I lost my live chat. Dun, dun, dun. There it is. Okay. Okay, perfect. So let me know on the outside chat if you can see this. Basically, this is going to be what we're going to be doing. This is actually a graph right here of the function e to the x. Okay, and hopefully you guys know what a function is. A function is just basically you put something in, you get something out. So the e to the x curve, it looks like this. Most people who have ever worked with an exponential is going to recognize this curve. It's found everywhere. It's found in compound interest. It's found in decay rates. Now, there's a more rigorous way to actually get what we're doing. Is using limits and integration. I'm not going to be going that route because this is complicated enough and I don't want to confuse people, and I haven't fully got that down where I'm comfortable enough to do it that way. So just kind of bear with me on that. But I just want to give you conceptually what we're going to be doing and then show you the math behind it. So what we want to do is we want to approximate the value of E using a Taylor series over and over again until there's a convergence on something. There's a convergence on what the value of E is. And each derivative we take is going to get us closer to that result. So we've discussed what a derivative is before. And in this particular case, if we take the 0th derivative of a function is defined to be that function. So if I have the 0 derivative of e to the x, it is e to the x. It is the function. So that applies to anything. But the first derivative, if we actually plot it out, when we do the Taylor series, which we're seeing, we're going to get different terms. The first term we're going to get is a 1 plus x. Then we're going to get these other terms. So don't worry too much what these mean. Look at the function, the plot that we're looking at. Oh wait, Steve, we're not showing over here. Wildheart can see it. Quartermaster, you can't.
I'm looking at it on my TV right now on the Xbox YouTube app, so I can see somewhat. I can't see the stuff on the far left, the buttons.
Which screen am I sharing here?
I see the graph that you showed me. Okay, yeah, now I can see more of it. There we go.
Steve, do you mind if I just give them a second of background about why we're using Taylor series?
Yeah, go ahead. By all means.
So
awesome.
the theory is if we have a sufficiently well-behaved function, and well-behaved in this context means infinitely differentiable and a little more, but uniform convergence, that kind of thing. Basically, what we're going to do is this. We want to approximate our function e to the x, which is called a transcendental function, but that's another story. We want to approximate it with these polynomials because polynomials are friendly critters. We know how to use them. And so what we're going to do is, first we're going to say, okay, what's the first step in approximating our function? Let's use a polynomial that agrees with one point, the point we're centering on the power series. The next step is, okay, let's make this a little more form-fitting. Let's say that the derivative agrees at this point. Then the second derivative, the third derivative, etc. Now, if this process works, eventually you're going to get, in the limit, you're going to get e to the x by the power series. But that's the theory. You start with You start with the function agreeing with the e to the x at one point, then the derivative agrees, the second derivative agrees, etc. ad infinitum.
And we have to make certain assumptions that you can actually take the derivative for each term, and we have to take the way we can actually find a coefficient for each one. So I'm going to show you those assumptions. But so for the first derivative, we end up with a tangential line on one point of the function, which is right here, evaluated at 0. This is where we're going to be evaluating it from. It's from the 0, the x equals 0. But as you can see now, this kind of gives us an idea of what the function is doing, but it's very coarse. It's not refined by any stretch of the imagination, right? Because we want to get it to 2.7. What is the value of e? 2.7185 something, if I remember correctly.
2.718281828, and then it changes.
There you go. So we want to get as close to that as possible. Right now, we're not really near that. We're at 1 something, right? So this is not going to get us where we want to go to get a good approximation. The next derivative they're going to be taking, right, is going to give us a little bit more approximation. So we have the 0th derivative, the first derivative, the second derivative, which are going to give us a parabola. Okay, and the parabola, if you guys remember, when you have a x to the squared, it gives us a parabola type shape. This is a little more form fitting. If you look here, this is actually following our initial e to the x curve a little bit more approximate, right? It's going to be a little bit closer to our function. Now, when we take the third one, it's going to get a little bit closer. I mean, this is almost spot on. And then as we take the fourth and the fifth, it's going to get closer and closer. These are closer approximations. Each time we add another term, we're going to get closer and closer to the e to the x function. That's the goal. So when you add up all these things together, you're going to get closer and closer. So we start off with basically the original function, which is f to the 0. The first derivative, which is going to give us the line. The second derivative is going to give us a parabola. The third derivative is going to give us this kind of shape. Every time you see a cube, x to the cube, you're always going to see something similar to this, where it approaches up from the left, and it goes upwards, and then continues on. And then the fifth, and then of course the sixth. And then again, as you do more and more terms, you're going to get closer and closer. And the goal is to take an infinite amount of terms and take a summation of that. Now, we cannot do that, obviously, in finite time. So there's mathematical processes of how we're going to take an infinite summation and get a result that will give us the actual function we're looking for, which is e to the x here. Okay? So we're gonna go right into it. We're gonna try to get the derivative of e to the x and show why it actually is e to the x. And we have to make certain assumptions to form the Taylor series to begin with, to explain to you why the Taylor series for e to the x is what it is. And so this is circular. I want people to understand that. This is not a formal proof. This is circular. I get that. But this is the only way I can really explain it in a way without involving more intricate processes to get coefficients and other things. So we're going to make two very, very simple assumptions. One, that the power series, okay, and the power series is the Taylor series. We're going to an exponent, right? We're raising something, so it's a power series, that it's going to be about x to the n, and I'll explain that, and that a derivative can be found for every order. And what we mean by an order, we mean a zero order derivative is the function, right? So if I have x, the function is x. The first derivative would be the first order. The second derivative would be the second order, and so on. So we have to make sure for this to work that each derivative exists for every order there is in the expansion. So those are two assumptions we have to make in order to make this work. I think by now we've kind of covered what derivatives are. We did this with Midnight the other day. He was spot on about it. I said, okay, let's take a function. Let's take a polynomial, and let's just take different derivatives of it. Drag, for example, if I have x squared, what was the derivative?
You said x squared. This would be 2x.
Okay, and then you take that. So the 0th derivative of x squared is the function, right? So the 0th derivative is x squared, right?
Oh, the 0. Okay, yeah. 0
Okay.
derivative. Yeah.
The first derivative would be the one you just said, right? 2x. Now take the second derivative. So
and it'd be just 2.
Just 2. Now take the third derivative.
Then it'd be 0.
It'd be 0. And every time you further, it'd just be 0, 0, 0. So it's a continue on, right?
Yeah.
So that's what we want to make sure. We want to make sure that each term, each derivative can be found for every order. By the way, did you give this link out to everybody? Drag? Did anybody wants? I'm not seeing who's coming in, so you're gonna have to like let me know. But if anybody wants to join us, and
I'll start inviting. Oh shit! Yeah, my bad. I see.
I know you wanted to get the link out to people, but you know, maybe G-Man wants to learn something. I don't know.
Let me see. Yeah, someone just sent me a message, so let me. Oh fuck! Is it?
All right. Now, I will give you fair warning. This looks a lot more complicated than it really is, although it is not simple. So it's one of those trade-off things to try to be able to explain it conceptually to where people understand it. Because this is daunting. This is Calc level 2 stuff. Now, to people like EO who teaches this stuff, he could probably do it in his sleep. But to most people, yeah, it's a little bit intimidating. But I want to see if I can explain it in a way where it doesn't really confuse people. Okay. So,
Steve, are you going to wait?
Yes.
Are you waiting, or are you going to keep going? Are you going to wait for the people to show up?
I was
just going to ask you, do you have paint? Or sorry, go ahead then.
No, if you want to put this in paint and give visuals, I'm okay with that.
No, I wanted to show everyone quickly this entire process of taking Taylor's series depends on something called the mean value theorem, which is a really cool graphical physical representation. But you don't have a touchscreen computer, right?
No, and I'm not going to get into the mean value theorem, but you could. But yeah, look at Pig wants a link. I'm fine with that.
I fucking hate mean value theorem.
So if you want, a link, you're gonna have to message Dragnot. What's that?
And one last thing, Steve.
Sure.
The one last thing. The proof you're going to use today works because we have something called uniform convergence, which allows us to take term by term differentiation. In other words, derivatives are a linear operator, but it's not clear that if you have an infinite number of terms that you can take term by term. In other words, the sum of the derivatives, the derivative of the sums. But the reason it works is because we have uniform convergence of the Taylor series, which is, by the way,
sorry.
Go ahead.
I was just saying, do you think
it's just a bookkeeping term? I just wanted to get out there.
Yeah. Do you think that maybe, excuse me, normally we would explain to people summations and partial sums first. Maybe we can do that. I can do that next time. I have no problem with that. They're not that hard. You would have to do like Cauchy sequences. I can't explain Cauchy sequences very well. But if people want to understand how to find the convergence of a sequence based upon the partial sums, the convergence of the partial sums, we could do that. It's a little bit more complicated, I think, than this, even though this looks a lot more complicated. But okay, so let's just dive into it. The Taylor expansion looks like this. Remember yesterday I had asked specifically EO to give us a form of how to do like a binomial expansion, right? And he gave us the whole combinatorial way that it should look using the exponents from Pascal's triangle, and how the exponents should look, and how each term the exponent is decreasing on one and increasing on the other. So A is starting off at a squared, then it'll be A, then it goes away, and then B will be like going up. So there's a form for these things, right? This is the form that we're looking for in the Taylor expansion. The compact form, it's called, is, by the way, you can see my mouse, right? Okay. I just on the outside. So this is the compact part right here. This, like right here, is the compact. This is the expanded part of it. And hopefully by the time I get done, this is going to make sense to you. Is there anyone else in here besides you, Drag?
Yeah, there should be Andreas.
I just want to see if anybody else is in here that maybe has not seen this before, and ask them how confusing it looks to them.
I've seen it before. I've actually seen it before. It's actually pretty useful stuff.
Okay, so I'll ask the outside chat. If anybody looks at this and maybe it looks confusing to them, hopefully by the end of this, it won't be that confusing. So what we want to do is, again, for the assumption, we want to evaluate as x equals a. Now, if you notice, if we make that assumption x equals a, what happens to these terms? Like, for example, in the expanded part, let's assign x0, right? Or excuse me, x to be a. what is a minus a? 0, right? And 0 times a constant is 0. Here's the same thing. A minus a is 0. 0 squared is 0 times constant is 0. All these terms go away when I make the value of x equals a. So what am I left here in the expansion when all these other terms go away? What's the only thing that's left? Anybody?
Hold on.
You're only left with an arbitrary constant.
You're left with an arbitrary constant, which is we're going to be assigning that the subscript of C0. Okay, so this is the only constant that's not affected by this because x is not a variable in this term. So in all these other terms, they go away. So I am left with just this. So I am trying to find each we can find a way to get each constant here because we know the value, or we know the value of x is equal to a. That'll go away, but we don't know what these constants are. So we have to see if we can actually find a constant for these terms to make this expansion work. So if I assign this to be a, I'm only left with c sub 0. That is my first constant in this equation. Okay, so given the 0th derivative, I'm only left with this first term. Okay, this is where we're going to get a little bit more confusing because now we want to take the higher derivatives. We want to take the first, second, third, fourth derivative, and it's a step-by-step process. So we're going to be using the power rule, which again, if you guys remember, the power rule for a simple function like this of an x with an exponent, you just subtract 1 from the exponent, you bring the exponent down to the coefficient, and then you have your derivative. So x squared, you subtract 1 from the exponent, giving you x to the first, which is x, and the 2 becomes a coefficient, 2x. Okay, so if you ever get confused there, just think of something simple like x squared. X cubed would work very similar. Take the exponent, bring it down to the coefficient, and subtract 1. So 3x squared would be 3x, excuse me, x cubed would be 3x squared, right? And then if you take the next derivative, 2 times 3 is 6. I end up with 6x because it's x to the first. And then you just have 6 and you have 0 again. So that's how this process goes. And I'm also going to be using Lagrange notation. Yesterday I used Leibniz notation because it's a lot easier for what I was doing yesterday. When you're doing Taylor series, it's a hell of a lot easier to use Lagrange. Would you agree, Yo?
Yes.
Yeah, okay. So I'm going to use Lagrange notation. Lagrange notation just looks like this. F of a here, where a is the argument to the function, that is just your 0th derivative. That's your function. This little prime symbol means I'm taking the first derivative. Okay, so if I have f prime of x, that's my first derivative of the function f of x. That's all that means. It's the same thing as saying d over dx, or if you have a variable y involved, dy over dx. That's all it means, first derivative. So let's take the first derivative, excuse me, of this initial form of the Taylor expansion. Okay. So when we take the derivative of a constant drag, what do we get?
Shit, I don't know. I have my mic still on. You said the first derivative of
a constant.
Of the constant, wouldn't it be the same constant?
No, it's 0. Remember?
It is?
Yeah, you take the derivative of constant, it's 0. Well, think about it. You take the derivative of 6x, you end up with 6, and then the derivative of 6 is 0.
And if I may, Steve, think about it more. Constants don't change, therefore the derivative has to be 0.
Yeah, there's no timer to change to a constant.
Oh, okay. That's kind of what I was thinking when I heard constant. I was like, well, yeah, it would be the same. Okay, so yeah, you take the derivative of that, and it. Okay, I got it. Yeah. I have a hard time remembering whether it's either or, that kind of thing.
Well,
I know that you can't do much with it either way.
Think about it this way. He's exactly right. Because all derivatives are a time rate of change with respect to something, right? Constants don't have a time rate of change. They're constants. So what's the time rate of change of 6? 0. What's the time rate of change? 10. 0. So all constants have a time rate of change of 0. So,
and here's yet another way. Constants are horizontal lines, and what's the slope of any horizontal line? We could ask anything.
0. Okay, that's how I can remember it. There we go. Okay, there we go.
Right. For people that maybe remember the other day, we were talking about derivatives. We're actually taking a derivative of slope at a certain point, right? And if you have a line, we can take the slope of that line, and that gives us the derivative. So as we take the derivative of the first constant here, that goes to 0, right?
Yep.
Okay, so I'm not going to put this in this equation because it's 0. right? I could write 0 plus, but there's no reason to. Now let's look at the second term, okay? This is, you got to remember, there's an implicit 1 right here, okay? So this quantity, this parenthetical group, x minus a, there's a 1 exponent here, and anything to the first exponent is itself, correct? So we just don't show that. It's just convention. Could you? Sure, you want to be wrong, but it's just convention. You don't need to show the first, just like you don't need to show a coefficient of 1. Every number, every value, exponent has a coefficient of 1 if it's just x, right? What's the coefficient of x? 1. Why bother showing it, right? So here I have 1. So I'm going to take, what is 1 minus 1? It's 0, right? So 0, what is these? If I raise something to the 0th power, do you remember what it is?
1, I believe.
1. Yeah. Very good. So this whole term becomes 1. Okay, you know there's 0 in here, right? Because x is equal to a, so a minus a is 0. So a is 0 raised to the 0th power is 1. Yeah, I know a lot of people get confused about that. Don't worry, it's just, you have to accept it. Okay, you just have to accept reality. That's the way it is. So what is your constant times 1? It's a constant, right?
Right.
Oh, I'm sorry, but I forgot. I gotta move the exponent down. So I actually got ahead of myself. So the first term goes away. This right here becomes C1, which is right here, right? This next term, I bring this coefficient down, so it's 2 C2, and then I subtract 1, leaving 1. So I'm left with 2C sub 2 x minus a, which is right here. My next term, bring the 3 down, 3C sub 3 x minus a. 3 is minus 1 is 2, and I left this term, and so on. So this right here, this whole equation, by the way, the difference between equation and expression, if anybody cares, is the equal sign. So an equation has an equal sign, expression doesn't. If I just say 5x, that's an expression, not an equation. But this right here is the first derivative of this, and since again we're sticking in x equals a, if a minus a equals 0, this term goes away, this term goes away, and this term goes away. So what am I left with here?
So f prime of a equals c to the sub 1.
Yep, exactly. So I've gotten 2 constants so far. I've got the first constant here, I know exists. I know I got the second constant here. We're going to keep on going and do the second derivative of that. Now the second derivative we can just get from the derivating the first derivative, right? We don't have to go back to the original and do like the third derivative kind of thing. Oh, Midnight, can you get Midnight in here? He wants to come in, please. I thought I sent it to you. I'm sorry.
I got him.
Okay, so the second derivative, we're going to do the same thing. So here the constant c sub 1 gets derivated. It goes away because it's 0, so I'm not going to put it in here. Here I have the exponent 1 that got brought down here. 2 times 1 is just 2. So I have 2c2. Because again, excuse me, this becomes 1. This right here, 2 comes down here, so I have 3 times 2, c sub 3. This exponent gets diminished by 1, which is 1. This leaving this quantity, and so on. Now, I'm actually leaving this way for a reason. I'm not showing 6 c sub 3 for a reason. Hey, Midnight. So this term here, I'll bring the coefficient down. I'll end up with 4 times 3. C sub 4, parenthetical group x minus a raised to the second power because it's 3 minus 1. Now, like I said, there's a very specific reason why I'm keeping it this way and not putting this as 12 and not putting this as 6. And I'll show you. I'll show you why. It's going to make sense as we keep going. And by the way, I have to give you guys warning. This is going to be a long hangout. So if you don't like math, you're going to be bored. But if you do like it or wants to learn, this is interesting. I'm actually enjoying this. So please try to bear with me. And I haven't made it too many faux pas because EO isn't like messaging me going, "Damn it, Steve, what the hell are you talking about?" So
I only took Algebra 1 and I can semi-understand.
Well, so Steve, you're doing fine.
What?
The only thing I'd add is in almost every power series, we center it at 0 to make our lives easier. The only one we don't is the logarithm series because logarithm's not defined at 0. You're doing fine. What I'm saying is you could probably make your life easier if you just go ahead and make a 0.
I'm going to get into explaining a Maclaurin series. I'm doing the Taylor first, and then I'm going to explain to get to Maclaurin, and then why it's easier. I'm starting ground up, buddy. But you're right. But I know. I normally when since we're doing x equals 0, we're doing it around 0, we could use a different type of series called a Maclaurin series. But I wanted to show people the Taylor series first, how we get to a Taylor to Maclaurin, and then use a Maclaurin series to actually get to the derivation of e to the x. So there's a method to my madness.
Get your energy drinks, folks.
Yeah, it's going to be a long hangout, brother. Okay, so this is my, if the first derivative was f prime, the second derivative is f double prime. Okay? So since all these other terms go away, because again, x equals a minus a is 0, this whole term here goes to 0. This whole term goes to 0. And I kind of wish in this particular program I could put a little arrow here. In nuke school, what we would do is we write an arrow through this, right? And then just put 0 up here. And there's no way to do this in this particular program. But normally when you, I don't know how EO teaches it. And again, this wasn't a college thing. But
we say it vanishes. It's really cool. Yeah, you're right.
Yeah. So what you normally do is you just put a big old arrow through this, usually like a red arrow or whatever. You just put an arrow through it, and then you put 0 up here. And this means this whole term goes to 0. It just goes away. Boom. Or you just cross it out. So I wish I could kind of do that because there's a visually appealing way of looking at it. This goes away, but I'm left with this. So the second derivative is equal to 2c sub 2. Okay, so now I've got 3 constants. I have c sub 0, c sub 1, 2c sub 2. Excuse me. Let's see here. Trying to remember how I got the. Oh yeah. Let's see. Through 2. How did I get the half here? I'm going back. Oh yeah.
You solve for C1. You divide both sides by 2.
Yeah, I solved. That's right. Okay. Yeah. So what basically I did was I divided each side by 2 here. Okay. So I'm ending up at C2 on this side, and I'm taking 2 and I'm just moving it over to this side. And by doing that, I'm just dividing this side by 2. These cancel out. Again, I wish this program allowed you to do it, because normally what you would do is you put what's called a vinculum or a horizontal bar. There's a slight difference, but a vinculum, this is right here, is called a vinculum or horizontal bar. But you put that there and you put 2 underneath, and these cancel out, 2 over 2. And then I'm left just with this constant. So I end up with 2f double prime of a over 2. So I know my constant now. Now, moving on to the next one, we're at the third derivative now. The third derivative would be the derivative of 2c2, which is 0 again. The derivative of this part of the term, which is going to give us 3 times 2c sub 3. This term is going to give us this, and so on. I think by now you can see the pattern forming. So I'm just going to divide both sides by 3 by 2 by 3 and by 2 on this side.
But you said the derivative of 2c sub 2 is 0?
Well, here the derivative of this is 0, right? 2c sub 2 is 0, right? It's a constant.
Oh,
correct?
Okay, yeah. Because
the derivative of this is here's 1 here, right? Yeah, so this is 1. So I'm just ending up with 1 times 3 times 2 times c sub 3. This gives us this term here.
Yeah, I forgot that c was representing a constant, not a actual a variable. Yeah,
right. Yeah, these c's are constant. That's I'm glad you brought that up. Don't get confused, because c is not a variable in these types of maths. C is a constant here, represents a constant. So don't think because it's a letter it has to be a variable. There's a mistake that a lot of people make in algebra. They see a letter that represents a number, and they think it's a variable. And I had that same guy that complained, there's an engineer that tries to convince people that 1 equals 0.99 repeating isn't true. He actually was trying to convince people that that these constants, because they are a letter, are called variables. They're not. And I'll even argue with EO on that. They're not.
No, I mean, the whole point, we use the last few letters of the alphabet to represent variables, and we use the first few letters to represent constants.
That's a brilliant point, yes.
In order to avoid this confusion.
And that is exactly what I explained to him. If you have A, B, or C, you're generally using them as fixed constants, and X, Y, Z, higher on the alphabet, you're using those as variables. I explained to him the exact same thing. So thank you. I'm glad that you pointed that out. Now, they may not always hold, though. That's a rule of thumb. Right, so let's not, because again, with the binomial expansion, a plus b, right there, we're using it as variables. So,
sure, okay. And look, the context is everything. And I remember a joke I heard in grad school. This guy was teaching a stats class, and he was using X's everywhere. What you do? He goes, "This is the problem when you name all your kids X."
This is a constant. I don't think I get it. I'm trying to figure it out.
We overuse letters in math. Like, for example,
I get
find
it.
the derivative. Okay. This is the problem when you name all your kids X. Never mind. Bad math joke. I've got a million of them, folks.
Yeah, my math joke was funnier with the whole derivative thing. Insanity. Okay. Oh, by the way, did I tell people in this hangout how this all started? My joke. I don't think
I think you told them last time.
9, Steve.
Yeah. So in this, but my joke was that got this all started was, what's the definition of insanity? Taking the derivative of e to the x over and over again and expecting different results. Now, to a math guy, that's funny. That's funny. So, all right. So anyways, now that we end up with the third derivative, which of course is f3 prime, right? We have 3 primes here. If I put x equals a again, what happens to this? This goes to 0. 0 times all this is a constant of 0, right? Here, it's not affected, so I end up with 3 times 2 times a constant, which is this. I subtract both sides by 3 and 2. I end up with my constant with f third derivative of a over 3 over 2. And again, there's a reason why I'm leaving this 3 as a 2. I know people can say, well, why aren't you reducing? Why aren't you putting 6 there? There's a reason. You'll see. And by the way, you're also going to notice that I don't use multiplication signs. This is called implicit multiplication by juxtaposition, or if you just want to say implicit multiplication, that's fine. But all this means 3 times 2. This is literally the same as a multiplication sign, but the multiplication sign is not shown. They're defined exactly the same way in mathematics. When you learn about rings and whatever, you're going to find that the way they define certain things, binary operators or partially binary operators like the derivatives, the division symbol, they're defined a very specific way in maths. And the multiplication symbol, it doesn't matter whether you show it or not. Multiplication is multiplication. So you might have seen these Facebook problems out there, like 6 divided by 2, parentheses 1 plus 2 equals something. And people say, well, it's 1. Well, I had beg to differ. It is actually 9 using standard order operations because implicit multiplication has the same priority as explicit. But that's a different hangout altogether. Frank wants to join. Okay. You got it. Okay. So the fourth derivative, does anybody walk? We're going to let somebody else walk this through it because this is the furthest I got, or I don't need to go much further to make my point on but somebody wants to do the fourth derivative. So let's take the next derivative of 3 to the 3 prime. So somebody want to do this? Who do we got here? Anybody?
My son doesn't shut up. All right. So where are we at?
You're going to take the derivative of each term here. So take the derivative of this term.
So that's at 6 times c sub 3. So that's going to be 0.
Okay. So we don't bother to show it down here. It's gone. Take the derivative of this one.
All right. So is that what? 4 times 3 times 2 times c sub 4.
Mm-hmm. So, times 1, which we don't show. We end up with this term. Mm-hmm. And then this actually I made a mistake right here. I just noticed.
So I was wondering. So I was wondering where that came from.
No, wait. This is
X1.
No, it's right. It's right. I capitalized this. That's yeah. Here we go.
Wait, is that supposed to be the next set of?
Yeah, this is not shown over here. This is not shown. Right. See this plus dot dot dot. This means it continues on. I should have noted that. This means it continues on. This is the first term. This is the second term. There's a third term. There's a fourth term. There's a fifth term. We're adding up all the terms to infinity is what we're actually attempting to do. So the next term in here would be this, and I showed it because I wanted to show people how you use the next term, but it's not shown here.
It's implied up there, but you made it explicit down there. Okay.
Perfect. So this all goes away because x equals a minus a is 0. So this all goes to 0 anyways. So I'm left with this, divided side by these, 4, 3, and 2. I'm left with c sub 4, fourth derivative of a over 4, 3, and 2. Now, here's where we start getting really cool. Therefore, I can actually say this. For every derivative of a, it is going to be over the n factorial. And remember what a factorial was. A factorial was, if I say 1 factorial, it's 1. If I say 2 factorial, it's 2 times 1. 3 factorial is 3 times 2 times 1. 4 factorial is 4 times 3 times 2 times 1. 5 factorial is 5 times 4 times 3 times 2 times 1. So this is why I'm showing it this way. You remember I told you that there's an implied 1 in every denominator in a fraction, right? So this is actually the 4 times 3 times 2 times 1. And what's another way of writing 4 times 3 times 2 times 1?
4 factorial.
4 factorial. That is why we can actually say this equation here. For C sub n, it is going to be equal to the derivative over n factorial with the argument of a. Once we recognize that, we can take this right here, and we can chug it way back here into our original formula here, okay? Because C sub n is now equal to this, and if you go back to here, I'm plugging in it right here. See what this constant is? All I'm doing is I'm taking this constant and I'm just showing it for we know what its value is, or we know what another way of expressing it is this, and I end up with this. And this is basically my original equation, right? With this shown for C sub n. Does it make sense so far?
Yeah.
You guys with? All right.
So far, so good. Just you may want to clarify that 0 factorial is 1.
0 factorial is 1. Yeah. Good point. In order to make this work in a Taylor series, 0 factorial has to equal to 1. It is defined to be that way. Okay. So just again, it's one of those things. Accept it as Jesus told you it. It's because you're not going to win an argument that it's 0. People have
also the multiplication thing you went over. I forget what it's called. That's just how you're taught now.
Yeah, well, yeah. I think, I think my daughter actually is learning it that way too. Right?
Yeah.
All right. So now that we have this expressed this way, again, this formula, we can do the expansion. Because remember, this is the compact form, right? But we want to know the expanded form as well. So the expanded form is going to look like this. Okay, and all we're really saying with this is that remember where I said that the 0th derivative of a function is itself, which is this, and then these right here are going to correspond to what we're showing like up here, right for the second constant is f prime double prime a over 2, c is f of f prime of a. That's all we're doing is we're just putting in the constants here. And we're just, instead of putting the constant, we're just putting in what we've already found these constants to be. That's why we wanted to find these constants. F of a is equal to c sub 0. F prime of a is equal to c sub 1. F double prime of a over 2 factorial is equal to c sub 3, etc. Okay? So all we're really doing is we're building upon stuff we've already gone over. That's how most of math is. We're just building upon things. And so if you lose a step somewhere, it can get very confusing really quickly because you don't know where to go back to, right? So this is what we actually end up. This is actually the actual formula for a Taylor expansion or Taylor formula. Now, what Eo was saying, we can make a Taylor series into what's called a Maclaurin series, and it's a lot easier to work with. And what we're doing is we're evaluating it at 0. So what we're saying is if a equals 0, and x equals a, which was one of our initial assumptions, then obviously, right, what happens if these two are equal? What does x actually equal? Because of the transitive property, right? X equals 0, correct? And then we're going to call that a special kind of Taylor series called a Maclaurin series. All Maclaurin series are Taylor series, but not all Taylor series are Maclaurin. Now that we're evaluating at x equals 0, we end up with this. All we're doing is we're taking what we already know here, and we're putting in 0 for a. That's it. Okay? That's all we're doing. Now, as we put 0 in there, we end up with this as the expansion, which is the same thing as this, right? But instead of having a, we have 0 in here, right? And we end up with a new compact formula, which is this. And the reason for this is because if you notice, by setting x to 0 and making a equal to x, or x equals to a, this part of the term goes away. Okay? I'm only left now with something like this. I'm only left with x to the n.
Sorry, Steve. You just mean a equals 0, because the point is
0.
We're going to approximate. Yeah. This is going to work for every single x, for every real x. Right. This will work. So you just meant a equals 0.
Yeah, you're right. So look at, if a equals 0, right? This equals 0. I end up with x minus 0, which is 0, right? So I just left with x to the end. That's where I'm getting this from. So this goes away. This part of the right here. This, yeah, I shouldn't have said the whole thing goes away. This a goes away because it goes to 0, and I just left with x to the end, which is right here. And this is called the Maclaurin series right here. This is what we're going to be using now. Now, this is how we're going to evaluate in order to see the Taylor series for e to the x. Now, again, this is where it gets circular, because you cannot use this in a proof to show that the derivation or the derivative of e to the x is e to the x, because I have to use the derivative of e to the x in order to find the Taylor series for e to the x. Okay, so I want very much to be clarified here. This is circular. Now, if we evaluate at x sub 0 of x sub 0 is 0, I have this formula, which is the exact same thing as here. The expansion was the exact same thing here. And the way I like to do it is this. I've done it a couple of ways. I found that this way right here, the second way I'll show you, is the way I prefer, but you can do it either way. What is going to happen is we are going to take the 0th derivative, the first, the second, and third, and keep going with any starting at 0, then 1, then 2, and find the derivative of each one and what it evaluates for at 0. Sounds a lot more complicated than it is. It really isn't. But I do want to note something real quick before I go on. When you have something like this, any one of these. What? I'm sorry. What?
Oh no, I was just going to ask something. I've noticed that you have f of x, f prime of x, f prime 2, f prime. Mm-hmm. Okay, once you reach to a certain point, do you just put a number? Because
yeah, yeah, exactly. We're actually going to show a compact way to write this stuff.
And so, sorry, Steve, you mean you have to have the parentheses, otherwise you mean composing the function 4 times. Sorry, it's nitpicking, but there's actually a profound difference between f to the 4th and f parentheses to the 4th.
Yeah, yeah. Oh yeah, and this is one thing I want to clarify. People may be looking at this going, well, wait a minute, if this is 0 times this, shouldn't this whole term be 0? No. Don't get confused with this and think that this is saying f double prime is times 0. That's not. This is the argument to this function. So it's f double prime of 0. Okay, that's where the kind of the math stuff has to come in. You're not saying f prime times 0 here, even though like right here you're saying 4 times 3 times 2. This is implicit multiplication with parentheses. This is not. This is a function with the argument being put into that function. Okay, that confuses a lot of people in mathematics.
So sorry, Steve, at the bottom of your table where you have f prime, f double prime, f triple prime.
Yeah.
You need an f super left parenthesis for right parenthesis, and it's actually really important because if you don't have the parentheses, that means the function composed with itself, which is something completely different.
Wait, you're right. So,
and by the way, let me tell the people,
this.
There's a reason Maclaurin series is so useful. Let's just ask the people, what's 0 times any number? Dreg, what's 0 times any number?
0.
0.
Right, and so what happens is in a lot of these derivations for sine and cosine, if you center it around 0, it makes the computations much easier. But we should note, this proof will work for any real value of a. That's what's so cool about it. But making it a Maclaurin series makes it a lot easier for the computation.
And also I'll note on that, I was going to get into this, but it's also cool that the Maclaurin series for any polynomial is the same series, only backwards. You'll basically end up, you always end up what you start with, only you'll see it was working backwards. But for example, if I say what's the Maclaurin series of x to the n plus 3, it's 3 plus x to the n. You can do it in your head. You don't need to go through all this. That's pretty cool. It's a neat little trick. But anyways, so this is what you want me to fix right here, right?
Yeah, and I'm sorry. It's not even me being pedantic. It's literally
no. It's right. No, of course, yeah. It should be that. Okay. So let me explain what this table actually is denoting here. The 0th derivative of the function is the function. We already established that, correct? So this is going to be the function that we get for the 0th derivative. So what's the 0th derivative of e to the x? Anybody?
Should be 1.
No. The 0th derivative of any function is the function.
Hold on.
If e to the x is the function, and the 0th derivative of any function is the function, what should we get?
I'm thinking of raising it to the power. I'm sorry. That's what. No, I got that.
Yeah. No, it's just e to the x, right? Because we're literally getting the same thing we put in. If you say what's the 0th derivative of x squared, it's x squared.
Holy shit, I got that right.
Yep, you're spot on. So my 0th derivative, remember, this is a 0 up here, if you think about it, okay? So my 0th derivative is the function, okay? Now when n equals 0, okay, What is e to the 0th power?
1.
1. We're evaluating this because remember, we're going to be doing a summation here. Remember, n equals 0 to infinity. That's, by the way, what the symbol means. We're going to be taking summation. When I'm evaluating this, I'm evaluating it at 0. So e to the 0th is equal to 1. Okay. So no matter if n is the first, so the 0th derivative, right? If this is 0, f0, 0th derivative of 0 is 1. So the second derivative we're going to take, right, with n equals 1. What is the second derivative of e to the x?
Oh, Steve, I see the confusion. You need superscripts there, buddy. Sorry, another formatting issue there. I think that may be why they're confused. You meant to say f to the nth derivative of f of x, right? That's what you mean there. That's why it's confusing. See how it looks all on the same level?
It's just because of the formatting, as you're saying?
Yeah, I think I wonder if that's why they're confused.
Yeah, it's
what it looks like. Because what it looks like you're saying, it looks like you're saying f of n times x.
Yeah, no, I'm not. Yeah, and I'm not trying to do that. What I'm saying, yeah, this is not f of n times x here, or not f of n times 0. What it actually is n here is the derivative number. Okay, so f0 would be f for 0th derivative, right? And then we're substituting that into x. So if this is the 0th derivative, we're just putting 0 here. Are you guys following? Actually, assuming no, I'm sorry. I wouldn't be correct. That the x is actually always going to be 0 because we're evaluating it at 0. Okay. So this is continuing. Maybe it'll make more sense. If the 0th derivative of e to the x is e to the x, if I take another derivative of it, won't I get the same thing back, e to the x again? Which again, we're trying to prove that. Which is again, this is why it's circular. But this is one of the things when you know it for a Taylor series, the derivative of e to the x is e to the x. The second derivative is e to the x. All the derivatives I'm going to get are going to be e to the x. Okay? So for any natural number between now and infinity, whatever derivative number I want. By the way, would you put this? Should I put this n in parentheses, or is it fine that way? EO?
No, the n has to be in parentheses. And
It does.
What you really want to say is for every n. You can't. N equals infinity is nonsensical. But sorry, go ahead.
Yeah, for every n. Well, this is bad form, but I'll get further into that. But yeah, you don't ever say x equals n equals infinity, but let that one slide. We'll call that a. We'll call that a.
As an upper index, sure. Sorry, go ahead.
Yeah. Well, they call it a. There's a special thing for that. Oh, come on, help me out. Yeah, what is it when you have it like a? You're kind of you're not sloppy in your nomenclature, but you're just.
Hand waving.
No, it's not that. This is actually a mathematical term for it. This bugs me when I can't think of something.
Here, let me just say something in support of Steve right now. This is.
Let me think of that. Let me think what it is. What are you talking?
So everyone who's listening, Steve is very brave to do this because this is Calc 3, not Calc 1, not Calc 2, Calc 3, and he's doing it from memory, and it's pretty impressive. So again, just him taking the risk and doing this as a public service.
3? I thought it was Calc 3. Oh, okay.
I did in Calc 3.
Yeah. I can't think of there's a term. There's a term that mathematicians use when you basically are a little bit sloppy in your nomenclature, but most mathematicians don't understand it. So
right, but
you're a little
the point
loose.
is here, you meant the nth term anyway, though. You
I
meant
did.
yeah.
Okay, so the point is that let me go to the next. Let me go to the right here because this actually shows a little bit easier. This is why I don't like a table like this. This is another way to do it. I like this way to do it. What I'm saying, all I'm saying here is that the a to the sub 0, right, which is my 0th derivative of e raised to 0, because I'm evaluating it at 0, is 1. For the first derivative of a sub 1 is the first derivative of e to the 0 is equal to 1, right? Then here a sub 2 is equal to this term. And again, if you look here, if you go back way back here, all I'm doing is I'm doing the same thing I've already discovered here. Here's my first thing. Here's my c sub 2 is equal to this, right? F double prime of a over 2. My c3 is equal to this. That's all I'm doing is I'm using that in a table type form. Okay, so I'm just saying here's c1, here's c2, here's c3, here's c4. Okay, so when you actually evaluate this as 0, e to the 0 over 2 is 1 over 2. Oh, excuse me, 2 factorial. Here, again, the constant is what I've found earlier is equal to e raised to the 0, because I'm evaluating it as 0, which is equal to 1 over 3 factorial. So basically, if you notice kind of a pattern here, I have 1 over 2 factorial, 1 over 3 factorial. If I took the next one, I'm not going to show it to you yet, but if I took the next one, a sub 4, what do you think the next result should be? If you follow the pattern. 1 over 4 factorial. Excuse me. Yeah, 1 over 4 factorial. So for every excuse me, for every a sub 3, a sub 4, that's all that's going to go down here. So a sub 5 is going to be 1 over 5 factorial. Now, if you want to write that in compact form, this is what you basically get. For all of n, it's going to be equal to 1 over n factorial. And we can express it this way. A sub n is for every n, evaluated as 0 is equal to 1. Now, I've written this 2 different ways, and maybe EO can correct me. I was going to ask him on this. One way to write it is this, for all of n. Right. Now, I wanted to show somebody a different way to write this. Did I get it right? Because I guessed.
No, it's beautiful. The only thing is, and this is again called a universal quantifier.
Existential universal quantifier.
As opposed to existential qualifier. The only thing, again, and I hope that everyone can understand what Steve means by f of n of 0. He means f super n of 0.
Yeah,
formatting.
Well, it is. I mean, I should be raising these, shouldn't I? Would that be easier?
It's good. No, look, Steve, it's
formatting.
Amazing that you're even doing this, and it's great that you were able to do it in such short notice. I hate to nitpick.
No, it's right. No, you're right. I mean, it's a formatting issue, but it's basically saying for the f of n, excuse me, not f of n, f raised to whatever power to give you the derivative. So f raised to the 0th power here, f raised 0 is going to be the 0th derivative when I'm evaluating 0. So I'm basically saying for all values of any derivative I have, with 0 being what I'm putting in for that value, I'm going to get 1, and that's what's happened here. I got 1, 1, 1, 1, 1, 1, 1, 1, 1. My numerator here is always going to be 1 every time. So the other way of writing with this little upside down a, people may see this in mathematics. It means for all of, right? The other thing they might see is a whole bunch of terms. One of the other ones they might see is a backwards e. That means there exists. So if you see like upside down n, backwards e, y, that just means for like all of n, there exists y. And this different set builder notation that you'll see in higher maths. But this is another way to write it that looks cool. It's one of those things that looks complicated, but it's not. So this is why I'm trying to demystify math. It's saying 1 for all of n. That's it. For any value of n, 0 to infinity, you get 1. Okay. So now I got this nice compact form right here. For any value of n, I'm going to end up with 1 divided by n factorial times x to the n. And I end up, when I expand that out, right? And let's expand this out real quick, because this is the most important formula here. This part of the equation right here is the compact form. Okay, right here. Let's start off with the summation here. N equals 0. What is x to the n? If I put in 0 here, x to the n is anything raised to the 0th power is.
It's going to be 1.
1. And if I put 0 here, 0 factorial is
0 factorial. I think, what is that? That's not 0. It's 1, isn't it?
Yep. And so what's 1 over 1?
It's going to be 1.
Here's my first term. Let's go to the next one. N equals 1. Okay, so x equals 1 equal to, or excuse me, x raised to the first power is equal to.
Oh, my son's talking. Is it 1 factorial?
X raised to the first power. X raised to the first power.
It's going to be 1.
Think about that.
No, Drake, x to the first power. So whatever x is, it's x. Good.
X. Oh, yeah, it's x. Yeah.
Right. It's x. And so and x over 1 factorial is x over 1. So I just left with x. Now, what you're not seeing here, now I could very well make this a little bit clearer, but you won't ever see it written like this because it's not how you do it. But I can easily put 1 over 0 factorial, x equals over 1 factorial, 2 squared over 2 factorial, if I wanted to. Let me see if I can I'll actually do it for you. Maybe it will kind of show you. Let me get to where it is on here. So 1 over, here we go. So if I say 1 over 1, Okay, if I say x over 1, actually, you know what? Let me do it this way, so maybe it shows even better. Actually, 0 factorial.
If I may, Drag, it's the same reason in organic chemistry, the vertices on aromatic rings simply mean carbon, and everybody knows that. In the same way, the implied coefficient's 1. Yeah.
So this is actually what it's looking like, okay? Right? Because I have n down here, right? So I have, you know what? Let me get this right. There we go. That's better. That's not the right bracket. One second, I'll fix it. Oh, did I just totally screw that up? One sec. Technical problems. One sec. Let me get this back to where it was. All right. Undoing. Here we go. So this should actually be down here. So I'm trying to get this to look right. So this is actually a formatting thing than anything else. So make sure I got this right. There we go. Now we're cooking here. So
so Steve, make sure they understand those exclamation points mean that the numbers are very angry.
Yeah. This is actually what this
nothing.
Well, they're not. Yeah. Hang on. Well, they're not varying. They don't even vary as n here. But what this is because I stick in 0 in here, right? The first term is 0 factorial, which is equal to 1. The second one is n equals 1. 1 factorial is 1. So I don't have to show these, right? That's why you leave them out. But if you actually look at it, it's 0 factorial, 1 factorial, 2 factorial, 3 factorial, 4 factorial. The next one would be 5th. And if you notice, it's the same factorial as it is the exponent, right? Because I have the exponent up here. So let's continue on. If n equals 2, right? Then I have with x squared over 2 factorial right here. And then x cubed over 3 factorial. Do you see the pattern? Everybody? Yeah, maybe. Let me delete this because I'm not used to seeing it that way. So
Son's talking in my ear. Sorry.
All right. So this is what the Taylor expansion should actually look like. Now we can get into the actually doing a proof of why the derivative of e to the x is e to the x. Okay. What we're going to do is we're going to start with let, and again, this is not rigorous. It's not formal. It won't fly, but it's just for explanatory purposes. So if I let the function e to the x be f of x equals e to the x, my formula for the Taylor expansion, right, which is actually the Maclaurin in this case, was for the e to the x is this, okay? Because we've already established it right here. Would you agree that this is what we're going to be using, and this is the expansion for it, which we've already discovered? So you guys with me? This is already we've already determined this to be the Taylor series. We've already determined this to be the expansion for e to the x. Now all we do is very simple. We want to evaluate it, which is the same thing I have written here, and I want to derivate. I want to take a derivative on both sides. So now I want to go back to the old nomenclature, the old way I like doing it, the d over dx. This is the Leibniz notation, because I find for this type of format, it's a lot easier to use. It actually shows easier too. So if I take d over dx with respect to e of x, and I do it on this side, I've got to do it on this side as well. Anytime you take a derivative on one side, you can take a derivative on the other side. So on this particular side, I'm left with the derivative of e to the x. Now on this particular side, when I take the derivative of this right here, what happens? What's the derivative of 1? Anybody? The derivative of constant is?
Said the derivative of 1 or derivative of constant?
Well, the derivative of 1, which is the derivative of constant.
Is going to be 0.
Okay, that's my first term right here. What's the derivative of the next one? X. This one's a little bit harder, but remember the derivative of x? Think about it using the power or whatever. What would you think the next derivative would be if I just say what's the derivative of x?
If you just said x, if it's just a variable.
Well, think about this.
1.
Well, hang on. What's the implied coefficient of a variable that doesn't show 1? What's the implied coefficient? 1. So I actually have 1x. Now take the derivative of 1x, and what do you get?
1.
There you go. Oh no. Wait.
If it's just a variable, if it's just x, then it would be 1. Yeah,
right.
yeah.
So I'm up with 1, right? Exactly. Yeah. So my second term right here is 1, right? So my first term goes, this one goes to 0. This one goes to 1. My next one is going to be a little more complicated here, but see if you can figure it out. What's the derivative of x squared over 2x, and why?
If I may, Steve, it'll be easier to ask them to find the derivative of x squared and then multiply by the constant afterwards.
Well, let's do it. Okay, what's the derivative of x squared? 2x, right? Would you guys agree?
Yes.
Remember, that's the one thing we love asking. What's the derivative of x squared? Anybody who's ever watching our videos should know it's 2x. So if it's 2x, right, and so I have a coefficient 2x, what happens here? What is 2 divided by 2 factorial?
It just gives you the x. I see what you're doing.
It just gives you the x, right? They cancel out. 2 divided by 2 factorial is 1, right? So I just left with x. Okay.
See, sorry, Steve. See, the 1 is turned into a 0. The x of 1. The x squared. The x squared over the factorial of 2 of 2. Since that's 1 times 2. The x, the 2 comes over. Yeah, okay, I see what you're doing.
Same thing we've been doing, right? For the next term, 3 comes down here, right? And this will become an exponent of 2. So I end up with 3 over 3 factorial, which is actually, when you simplify it, is going to give you x squared over 2 factorial. By the way, these factorials are screwed up. I just noticed that. Let me bracket these so they're actually makes a little more sense there.
I think these 2 videos need to be sent to Edgar.
Yeah, no kidding, right? All right, there you go. That makes more sense. Now, since this is what we're ending up with so far, I can get rid of this 0. Would you agree?
Yeah, I
right?
suppose
it doesn't need to be there. 0. Okay, so I'm ending up with d over dx of e of x equals this, right? Well, does this look familiar? This is kind of what we wanted to evaluate, take the derivative of the first place, right?
Yeah.
So the derivative of this whole thing gives us that whole thing again.
Pretty much.
So therefore, the derivative of e to the x, and we've established e to the x is equal to this, right? Because right here, e to the x is equal to this. The derivative of e to the x is e to the x. QED.
Everybody clap. Everybody clap.
Circular reasoning. It's valid. Circular reasoning.
Can anybody tell me what QED stands for?
Quod erat demonstrandum, which was to be shown.
That stands for that to be which was shown. So anyways, this is not a rigorous proof. I point that out, but it explains to people why the derivative of e to x is dx. And I didn't realize this was like this high of math. To me, I don't think it's that complicated, but for people that never had it, I can understand people going, "Oh my God, math!" But there's a reason why this stuff works, right? There's a method to the madness, and I don't want people to be scared of it, because my math, I'm not gonna lie, and you guys you're gonna really think I'm being deprecating, but I'm not. My math skills suck. I am not good at math.
Oh, stop, Steve! You're lying.
No, dude, I've had to have it, and I did it decent in it, but I am not a math person. I mean, it's not. But I grasp the concepts, and all I wanted to do here was explain to people the concepts. And one more thing before I stop screen sharing, let me show you exactly what we were doing here. My addendum. This is the value of pi. Or it's not pi. E, right? 2.718281828, and it goes off infinity. Well, it goes off expanded notation, which is called an infinite decimal expansion. It's not. This is not an infinite number. The reason it's not an infinite number is because it exists between 2 finite numbers, right? I can say it exists between 1 and 3. I can say it exists between 2.5 and 2.8, right? So it has to be a finite number. So what we're doing is we're making approximations. So by using this expanded notation that we had, what we really get is when we actually do the math, we stick in values for this stuff, right? Remember I told you that each one of these things evaluates to 1. This goes way back to right here. Whenever I put in something, it's always going to give you 1, right? Well, this is what we get. This is where the magic actually comes into play. 1 plus 1 plus 1/2. That's what this evaluates to. Plus 1/6 plus 1/24 gives you this. And when I add another term, 1 over 120, like 120, it gives you this. And if I keep going, it gives you closer and closer to the value of E. And if I just did it an infinite amount of times, what do I get? I get the value of E. So what we're doing is we're just adding terms over and over again, summing them up to infinity to get the constant E. And pi works a very similar way.
So, Steve, if you notice, the first three numbers are always 2, 7, and 1. Unless, wait, never mind.
Yeah, but that's well, it's 2, 7, but that's only because I'm adding these terms, right? If I just started with the first term, I'm approximating at 1, right? And if I add the second term, I'm approximating, I get 2. The third term, because it's 0.5, I'm at 2.5 with these 3, right? If I have the next term. Now, if you guys remember back to the beginning, what is this actually representing? What is actually each of these terms representing? That goes back to, let me minimize this. That goes back to where we started again. This is my function, right? My very first derivative is 1 plus x, right? Which is just, here 1. It gives me a line. Again, I'm at this point here, right? Tangential line. I'm at 1. So if I were trying to approximate an infinite summation to get to 2.7815, whatever it is, I have to start somewhere. I'm starting with 1. So I'm getting there, but I'm not quite there yet, right? I'm not anywhere near 2.7. So I take another one. I take the second derivative. Okay. Well, now I'm getting closer to this, right? I'm getting more and more approximation. I'm getting a lot closer every time I add another term. And every time I add another term, I'm getting closer and closer. So if I added an infinite amount of terms in the series, Midnight, what do you think I should actually get? I should get the original function, correct? Yeah. There you go. There you go. That's how you actually do a Taylor series. That is actually how to take the derivation. And I thank you all for watching this. If any questions, hopefully I can answer them. I'm actually kind of proud of myself, to be honest with you. It's been a long time since I've done a lot of this stuff. People don't seem to realize that I have had some education. I don't talk about it often, but when the
you don't want to brag. You don't want to brag.
It's just like the Clown Car Posse and these other people that kind of talk about us. They don't realize what we actually had. They don't realize what Drag has educated himself with, what Sam has educated himself with, what Jade has educated himself. And I will say this, and again, I usually very self-deprecating. We are epically and eons beyond their level on a lot of things. And I will be happy, and I'm sure everybody else would be, to try to raise people up to the understanding this kind of stuff. Yeah. That's what I like to have happen in the Greek community. That includes the Clown Car Posse and everybody else, but they don't seem to want to learn. But the mere fact that I was able to actually in a day make this presentation and go over it, I can guarantee, unless you've had this before, you would not be able to do this. So,
I mean, Steve, it's like riding a bike. You know what I mean? You never really forget.
Oh, you do. I tell you what, I had to go. I remember this. I think I could do this, but it's something that shows that obviously, I'm not just talking my ass. I've actually had some maths, but I'm not at the level like EO. But the fact that EO admired that I was able to make it through this, that means a lot to me. I'm not going to lie. It means a lot to me. Thank you, EO. So we got any questions on that?
Yeah, it's great.
By the way,
I'll just say, great presentation, and you showed that the power series converges to e to the x for every real number x. To your point, we're happy to learn from anybody. If anybody from the internet wants to present an area of their expertise, I'm sure we'd all show up too, right, Drag?
Of course. I mean, it's I can't tell you how much stuff that I've actually learned from folks, like Jade, like Fiona, 2 people who are Christian, by the way. But just so happen to know a lot about math and science and some of the other topics we're interested in. And hell, after this, I think Richard's supposed to be hosting something on his theological position, I think for contingency, if I'm not mistaken. So
that's gonna be interesting. Hey, but Drag, let me ask you a quick. Honestly, you and I have known each other for a while, and it's gonna sound weird, but are you a little bit surprised I was actually able to do something along those lines? I mean, I know that you know my background, but I don't ever talk about this stuff. I don't give presentations on this stuff. The last one I did was a Polonium Halo stuff. But are you at least kind of a little bit surprised that I'm actually not?
Yeah, I mean,
I'm not. I mean,
it was at least Calc II, and for 20-something years, yeah, that's pretty amazing. You kind of just pick it back up in a few days and go back over it and work through a Taylor series and then
like
go
I
through
said,
the Maclaurin series. Yeah.
So what do you guys want to see
harder.
next? What do you guys want to see next? I mean, I'm enjoying this stuff. So what do you guys want to see me do next in the next presentation tomorrow or the next day?
Okay, the Taylor series of the sine function or cosine. You know what I mean?
Do you guys want to continue with high? Do you guys want? Well, first of all, I hate trig. Trig is my weak point. I'll leave trig for other people. But there are certain Taylor series for sine and cosine and all that. But do you guys want to stick with Taylor series, or do you want to learn something else in mathematics that's kind of an interest?
Well, I leave it for the audience to decide, or whether they want us to handle the topic. I know that once I get into Chem 2, I'll have a little bit more better. I will have a better background in chemistry, so I can probably talk a little bit more about that, because I know King Crocoduck wanted to hear about that. But you know, maybe me and Andreas could do something, because I know he's taken biochem recently.
That'd be awesome.
What's wrong with? There was something wrong with Mike. But Steve, do you know anything about matrices?
I can do some matrices. Sure. You want to go over matrices next time? How about we do matrices?
I mean, learn. Yeah.
All right. Have you heard of something called Kramer's rule? There you go. How about that? EO,
you want to go all the Sure, but you want to go all the way to determinants, and that before introducing linear operators? You'd be jumping right in the middle of things.
Well, yeah, no, I mean, obviously, yeah, I'm not going to jump right into Kramer rule, but I mean, if you want to do how to determine it, how do you find the determinant of a matrix? What a matrix actually is. Now, again, that is going back a long frickin' time. That is going back to 1992 for me. So, yeah.
You know what, Steve? I can see your dream project. You could start with matrices, and then work up to tensors, and then you and Han Solo could solve Einstein's field equations.
Yeah, well, you mean go over them? Sure. Hang on a sec. 1 sec. Continue on. Give me a minute.
Sure. Right, so fellas, do you guys know about the birthday problem? Midnight, Andreas?
The birthday problem?
Okay. So the next time you're in a group of 23 or more, you with me? 23 is the magic number. You guys with me?
Yes.
Okay. Feel free to make a bet. If it's 23, make a small bet. If it's 30, make as much money as you have in your bank. This is how it works. Imagine you're at a party, and there are at least 23 people. What are the odds that any two people will have the same birthday? Now, be clear, I'm not saying someone will have the same birthday as you, but any two people in the group will have the same birthday. You guys with me?
Well, I mean, I guess you could say it's 1 in 23, but it's probably wrong.
No, there are 365 days in a year, right?
Well, right, yeah.
Okay.
Right.
So this turns out to be one of those cool things with what Steve mentioned last time with the product symbol. Most people think that you need a really huge number like 182, but it turns out that's not how it works. How it works is, okay, the odds of two people not having the same birthday are 1 minus 364 or 365 times 363 or 364, if you follow the logic I'm using. But anyway, it turns out we can do a presentation next time where if you have just 23 people in the room, there's a 52% chance that any two of them have the same birthday. And if you get all the way up to 30, there's like a 95% chance.
Really?
It's very counterintuitive, yeah.
And what's cool is people who don't know the argument will say, no way, man, you need 182, like half of 365. You follow? And so you could win. You could easily win a bet, Dreg.
That's interesting. That's very interesting.
The math is actually easier than what Steve showed today, and we can do that next time if you'd like.
This is actually, you know what's funny is this is kind of high level math that we did. You guys, if you guys understood what I just said, you guys are way ahead of
some of it. Yeah, some of it.
You don't have to like master it. No,
well,
but
I mean, that's because if you know how a derivative works, I mean, it's just doing a series of derivatives and then defining understanding what the proof is. I mean, I don't.
You're just finding the derivatives and evaluating it at zero. That's it. That's all you're really doing. Now, again, I would love, and I would let them, if true empiricism ever wanted to come in and give a lecture on something like this, I would be totally down for it. I would listen, or somebody along those lines. I'm all game for that. But let's do matrices next time. I have to do some refreshing work on it, and I know there's a lot of people that can do it better than I can. But the thing with the problem I'm going to run into with matrices, and maybe you can add some insight on this. Is it difficult, do you think, for them to jump into matrices without learning linear equations first?
Yes. In other words, I wouldn't, because otherwise they'll have no connection to what they're doing.
Right. That's the issue that I see. because it's going to be disjunctive. You know, kind of if they're not going to understand the relationship of matrices to solving a set of linear equations. So how about instead of doing matrices first, how about I do more of a presentation on solving a set of linear equations?
That'd be great. You know what? Here's a great problem that, you know, from ancient times, there are chickens and sheep in a yard. And the total number of animals is X, and the total number of legs is Y. How many of each animal are there? So you have two unknowns, and you need two equations, and like that, you can really motivate the discussion. It's a lot of fun.
Okay. Yeah. Now, I'll think about something. And eventually, like, because linear equations, they're kind of easy for the most part. I mean, you know, but we can do linear equations, and then we can do matrices, and then at some point, I really would like to get into differential equations, but unfortunately, that's where my I'm about to say expertise. I have no expertise in this area. I'm not a mathematician.
"Quote unquote" expertise.
Well,
that's my knowledge level. I can do very simple differentials. If you give me something like what is dy dx equals like negative y over x, I can solve that one because I know it's a first order partial. Excuse me, first order separable homogeneous linear differential equation. Those are pretty easy to solve. Once you leave that, then I'm like, oh, gee. So,
Steve, can I make a suggestion? Do you remember that young man you had during one of those last after shows? He was a stats teacher. He was excited to meet you. Yes. What you should do is have him on and discuss confidence intervals. And I mean this because it's really important people understand why polling works. In other words, the population of the United States, the voting population is about 200 million, I want to say. Yet phone samples are only about 800 to 1,100. And so we can easily explain to people why that is. And that might be a good lecture to have. I mean, I would leave that to
somebody else, though. I do not even want to dive into to statistics, even though I had statistics and I understand confidence intervals. That's like Sam would be really good to give something like that. But I don't think he's really interested to give those lectures. But somebody along the lines that or hog tie, I don't like stats, so I would not be somebody that enjoys doing that kind of presentation. But I think you're right.
How about teaching Edgar the Pythagorean theorem without shaming him? Let's just bring him in and show him how to do a few examples.
Who, Edgar?
Or anyone who wants to learn. I mean, this is fun.
Well, I mean, like I said, if anybody else wants to pick up the torch and do something, the channel's open here. It's a great debate community. We don't have a lot of viewers on this channel. A lot of people know we have a separate channel, but this is where I want these kind of things to be, so people can learn. And when people say, "Oh, well, people don't learn anything on Steve's channel," well, okay, well, you can believe that all you want, but at the same time, come over here. We'll educate you on something.
Yeah.
All right, so that sounds good. Okay. All right, so anyways, let's end this. I will work on a thing for linear equations. Excuse me. And then matrix, and then, like I said, somebody. You know what? Maybe I should challenge somebody like Drag. Maybe he can do. Maybe he can explain a presentation of very simple quadratic equations, because that would help because of defining the determinant or things like that. Sure. If you explain maybe quadratics, that would actually be okay. Very simple ones.
I'm gonna have to do them for Chem 2. Actually, that's part of the,
you have
part of solving problems.
You're never gonna get out of school without not having to learn quadratic equations.
I mean, I got the fucking formula memorized for some reason. I don't know why. I didn't do it intentionally, but I think toward middle school, then when I started getting to high school, is when it started getting really ingrained into my mind. So
it's nice when you don't have to use it, though. There's a lot of times where you don't have to use it. It's like, oh, well, this is simple. I can just do this, but done. But
well, I think that it's not the hardest part. Isn't really transforming
the discriminant, by the way, not the determinant.
I mean, but it's like to actually apply the formula is not really the hardest thing. Is to determine, because you end up getting two values, and so determining which value is the correct one. If you're trying to determine like a distance or something, obviously you're not going to have a negative distance, but you would be surprised who picks the negative number.
Yeah, you're exactly right. You have to think of these things in real world applications sometimes, right? Even though you're going to have two roots, right? But if you can like do a presentation where you can show somebody what the discriminant is. Do you remember what that part of the equation is?
The discriminant. Not.
Oh, wait.
Do you remember the quadratic formula, Drag?
Yeah.
Do you know the
part
I remember
that.
Okay, hold on.
I know it. Yeah,
okay.
Of course. Okay. It's everything under the radical. So everything under the radical, which would be b squared minus 4ac, that's called the determinant, right?
Discriminant.
No, it's called discriminant. Yeah, the determinant is for matrix. But you got to remember that
if it's zero, it's Sorry, Steve, go ahead.
That formula that you have memorized, there's actually a general formula for that. It's a lot easier to memorize. It's real simple, actually. It's nobody, you'll never forget this. This is ax squared plus bx plus c is equal to 0. That's the general form of any quadratic equations. And once you learn it makes sense why that actually is. But you just take
repeat the formula.
It's a to the x squared plus bx plus c equals 0.
Oh. Yeah, it basically lines up all your variables so that you can apply the formula to begin with.
It makes a lot of sense when you start there, because one of the things you learn in college algebra way back when, you learn how to actually plot a function. For example, if I say what is the function is x squared, when you plot that, if you've ever had math, you exactly, you're going to get a parabola. And where's the apex of that parabola going to be?
If it's x squared, okay, do you mean vertex or vertex?
Yeah, the vertices.
Oh, 0, 0.
0, 0. So it's basically on 0, 0 of the xy of the Cartesian coordinate system, right? So when you start mapping these things out, and maybe somebody else might want to do a presentation on this, when you start adding things to that, when I add a coefficient, when I add x squared plus 2, all I'm doing is I'm changing either the position of the parabola with respect to the axes, or the degree at which the parabola opens up or closes. It's eccentricity. Is that what's called, EO? If I remember correctly.
No, you're trying. It does have eccentricity, but you meant whether if the leading coefficient is positive, it opens upward. If the leading coefficient is negative,
downward.
It opens
Yeah,
downward.
that's right. The way that's exactly. So
you
you're
know
right.
what I found?
So
if it's x squared of a positive coefficient, it's going to open like a U, and if it's a negative coefficient, it's going to go the other way, like upside down U.
Yeah, you know what I always found weird. Sorry to interrupt you. Now, the track, like say you have one divided, let's say 1 divided by 50 x squared. It actually opens up the parabola. It makes it wider.
Yeah, I forget
odd.
Yes,
I forget what changes that. What changes that? I know. I mean, I remember doing shifting, right? The inflection of the parabola, the shifting of it. What actually changes the
right, so we have vertical stretches, vertical compressions, horizontal stretches. But so, Midnight, to your point, yes, it does flatten it out, but you can change the scale and that's a good point. When we're dealing with the limit, all that matters is the power, not the coefficient. So in other words, if you want to compare x squared to x squared plus 50 million x plus 3, as you go to infinity, they look like the same function. I mean, the limits, if you divide one by the other, the limit will still be the ratio of the leading coefficients. This is really technical, sorry. But my point is, all that matters for polynomials is the degree of the polynomial. Anything else after that doesn't matter in terms of growth.
Yeah, so for the parabolas, for x squared, you're going to parabola, but for like x cubed, you're going to end up with that shape that I showed you people earlier. It's going to approach from the left. It's going to have that little, turn. It's going to go back, turn the other way, and then continue on as it goes from the left to the right. So you learn all these minimum and these maximums and Newton's. You have to find the roots, right? But that's all college algebra stuff. So. Oh, we're gonna be over in about 1 minute here. So
we have a question in the chat. What has Taylor done? What Taylor had done was to reverse the process from known constant to arrive with the basic assumption of derivatives. That's for Mr. ID.
Wait, what? Edgar is that? Okay, now I'm lost. What?
I'll copy and paste it in the chat.
Hey, we had our first ban. We had our first ban on the Great Debate community. Yay!
Oh, that's so the dude spamming.
If you ever see anything like that, where somebody's, don't say what was said, but if you ever see anybody saying those kinds of things, don't even wait. Just ban them right off the bat. I don't care who it is. Yeah, just
wait.
Ban
What?
Don't worry about it.
I was too busy reading Mr. ID's comment. I'm trying to understand.
I mean, get Edgar in here.
No, we have people coming in.
Yeah, all right, yeah.
We're at our threshold there, but I really want to do more of these things. I actually enjoyed this, guys. Thank you. I know we only had 10 viewers, and I want people to realize it's not just for the views, it's not just for the Patreon, it's not just for the amount we get from making videos, which actually it's actually not that bad lately. It's not great. I mean, a couple bucks a day adds up, right? But I did this because I enjoyed it, right? And I think that's why we all do things.
Yeah.
Yeah, and so I want people to realize that that we do these things because we enjoy it. I go to my channel because we enjoy it. But if anybody ever asks you, what from the great community, that you can learn, just refer them back to this kind of stuff. I never want to hear, Ronnie or G-Man or any of these guys say that we don't explain, we don't educate people, because this is what the great big community is going to be doing. It's educating people on this type of stuff, and from a very basal kind of point of view, a very lay person's kind of point of view, because I think that if a lay person could explain it like myself, that somebody can understand it and at least get the gist, right? This is not going to make you a master of math, but it's a gist. Anybody like EO or General Han Solo could do this, but I think it's cool that I can. And when they say that I don't have any education or that I don't know what I'm talking about, just refer back to this or my polonium halo stuff. Clearly, I'm not a complete moron. But anyways, guys, thank you for watching. And Richard, I know you're going to have your hangout next, so people keep watching. And